This figure shows you the Jablonski diagram, okay, which illustrates the different energy levels that electrons go through during the whole process of excitation and relaxation. So excitation pertains to the um, transitioning of electrons from a lower energy level, such as the ground state, to a higher energy level. So as what we mentioned last time, okay, an electron, say, coming from the ground state here, okay, so these electrons, okay, would be able to go to the next energy level, say up to here, if you're able to um, expose it, no, with an energy equivalent to the energy differences between these two energy states. Okay, now you refer to this type of transition as electronic transitions. Okay, so you have electronic transitions. All right, so that's a transition in between the ground state. All right, well, you call that your S sub 0 to a higher energy state, say the first singlet energy state. Now, in between, okay, these two electronic states are virtual vibrational states. So when electrons are made to um, be excited and just go through these energy levels, you call this your vibrational transitions. Okay, now if you look at the molecules that undergo uh, only vibrational transitions will have their molecular bonds vibrate, no, and this is what we utilize in IR spectroscopy. All right, what else? Then in between these vibrational states, you have what you call rotational states. Rotational. All right, and if electrons are made to, again, be excited enough to go through these rotational states, it pertains to a change in well, basically the nuclear spin, no? And this is what we utilize in NMR spectroscopy. Okay, now, sorry, okay, so looking at the different energy levels, we can see that let's erase this first. Okay, all right, so what can we generalize about this, no? The energy required to invoke electronic transitions would be greater than the energy required to invoke vibrational transitions, and this one would be greater than the energy required to invoke rotational transitions. Okay, now if you expose your sample with okay, with UV visible light, all right, UV visible light, you will be inducing all of these three. All right, because if you induce electronic transitions, automatically malalagpasan mo na yung vibrational and yung rotational energy levels. But if you expose the sample in IR radiation, you won't be able to induce electronic transitions. Alright? Uh, what you can induce is only vibrational and rotational transitions. Then finally, if you expose your sample in radio frequencies, okay, under the influence of a magnetic field, which is what we do in NMR spectroscopy, what we induce is your rotational transitions. Okay. Now, so again, the process by which electrons get excited is what you call absorption, no? So when your electrons absorb EMR, okay, they get excited and they are promoted to higher energy states. Now, after being excited, electrons will have to go back down to the ground state, no? Hindi pwedeng excited lagi, no? For a very long period of time, no? So there are two ways by which electrons could go back to ground state, no? And both of which will involve a release of energy. All right? So the first one is what you refer to as non-radiative relaxation. So as the name implies, there will be no emission of radiation. So the absorbed energy will be released primarily through heat, no, in the form of heat. So the other one is via radiative relaxation. So as the name implies again, this is the relaxation, no, of energetic electrons which is accompanied by the emission of radiation. Okay, so you have your fluorescence and phosphorescence. Okay. So first you have internal conversion. So this pertains to a non-radiative process of relaxation where excited state couples to upper vibrational level of lower electronic energy levels followed by vibrational relaxation. Okay, so as seen, sorry, where's the pen? So as seen in this figure, no? So for example, an electron is located here. Internal conversion happens when this electron in the lowest energy level of this particular excited state, okay, transfers to a vibrational upper vibrational level of a lower electronic state, no? So this is what you call internal conversion. Vibrational relaxation, on the other hand, is a non-radiative process by which the upper vibrational levels lose energy and go to the lowest vibrational level within a given electronic state, both of which are very fast, no? Around 10 to the negative 12 of a second. Now, both of these routes of relaxation is related, is sorry, not related, but something that is manifested, no, by an increase in temperature in the sample. So if you're doing solution based analysis, okay, uh, when this occur, you can observe this as an increase in the sample's temperature. All right. these routes will also occur if your excited molecules will collide with other molecules, no? So these non-radiative processes are quite efficient, all right, in lowering the energy of your electrons and bringing them back to the ground state. Okay. Now, intersystem crossing. This is quite interesting. No? So, by definition, this is when the lowest vibrational level of the first excited singlet couples to the upper vibrational level of triplet state, followed by vibrational relaxation. All right. Now, uh, maybe you've discussed this in your quantum chemistry, no? Yung difference no singlet and triplet state, no? So I leave that to your phychem instructor. But basically, what happens is this, okay? If you have, say, your electrons, you should remember that electrons, whenever located in an energy level, okay, it will still follow yung three basic rules, no? Yung Aufbau, Pauli's, and Hund's rule. Alright? So basically sa Pauli, sabi niya, pair of electrons, okay, will exist as electrons of opposite pairs, no, per orbital, no, yung tawag natin. Now, when an electron gets excited, say this one, no, goes here, it retains its spin, okay, but once it undergoes intersystem crossing, intersystem crossing, there will be a reversal of electron spin. Alright, but once it goes back to the ground state, it will retain, it will revert back to its original electron spin. Alright, so that is intersystem crossing. Now, radiative processes, no? So the first one, you have fluorescence. So for fluorescence, this is when your electron transitions down to one of the vibrational levels of the ground state, giving up energy as photons. Now, since this is a direct, no, a more direct route, all right, this is quite fast, no. It will occur less than 1 second. No? So this is really very fast, no, fluorescence. In contrast, phosphorescence is also a process wherein you also have this emission of radiation, no? And phosphorescence will occur via, no, so the electrons would need to first go through intersystem crossing. Okay, so again, this will also emit radiation, but since the pathway from absorption, intersystem crossing, and phosphorescence is much longer compared to your fluorescence, in effect, phosphorescence has a higher lifetime. Okay, so phosphorescence can go from a few minutes to hours. All right, so fluorescence, okay, for fluorescence to occur, if you want this to occur, you need to have a continuous light source. Okay, so you need to have a continuous light source. All right, so if you turn off the light source, fluorescence will cease, no? In contrast, for phosphorescence, if you illuminate the sample that can undergo fluorescence, even if you shut down the light source, phosphorescence will still go on. Okay, and you have to remember this because this has consequences with regards to the instrumentation and the analysis proper. Okay, so absorbance, okay, is basically the measure of how much EMR was, or energy of the EMR was absorbed by the sample. Okay, now basically what we are computing first is the term called transmittance. So transmittance refers to the amount of transmitted radiation. Okay, so transmittance is simply the ratio between the intensity or the power. Modern books will prefer to use power instead of intensity. So this refers to the intensity or power of the transmitted radiation over the power or intensity of the incident radiation. Okay, so basically, if you have a transmittance level of 1, it means to say that there was no absorption. Okay, so that's the maximum value for transmittance. So as your sample becomes more absorbing, all right, your transmittance goes lower, and that amount that was absorbed is measured by the term absorbance. But absorbance and transmittance is actually related via a logarithm, no? So we know that absorbance is equal to negative log of the transmittance, or if you're using percent transmittance, which is as t times 100, then you can make use of this formula here, no? 2 minus log of percent t. Okay. Nevertheless, no, even though logarithmic yung relationship, what we can establish is that the higher the transmittance, the lower the absorbance, and vice versa, of course. No? The lower the transmittance, the higher the absorbance. Okay? Do not forget how to interconvert transmittance and absorbance, because in the board exam, one way to make a question a bit difficult, especially in computational, would be to give transmittance values, no, or percent transmittance values instead of absorbances. Okay. Now, another interesting fact about absorbance. Oh, I forgot to include it here. Also, remember, absorbance is related to your directly proportional to your concentration. No? So when you say it is directly proportional, if we're going to plot concentration versus absorbance, you will get a linear curve. Okay. Now another interesting fact about absorbance is that absorbance is additive. Alright, it's an extrinsic property, and one important consequence of the additivity of absorbance is the technique known as the analysis of mixtures, no, for absorbance UV-vis absorption spectroscopy. Okay, wherein we can simultaneously determine the concentration of two analytes, no, in a sample, no, two absorbing analytes in a sample. So yung mathematics nun, calculation, and we'll show that later, no, but it involves what you refer to as your simultaneous linear equation. Alright, so this is the famous Beer-Lambert's law. Okay, so this equation shows us the relationship between absorbance, okay, the measured quantity in instrumentation, and the concentration, no, the quantity that we are determining. Alright, so AB or epsilon B serves as your proportionality constant, no? So that's one thing you have to remember in instrumentation, no? Yung computation. Remember that the instrument response is almost always directly proportional to your concentration. So when there is direct proportionality, you always have this proportionality constant. Now, in different instrumental techniques, say chromatography, okay, or fluorescence spectroscopy, okay, the form or the variables in the equation may change, but nonetheless, this format remains the same. No? You have the response variable, the instrument response, the concentration being related by a proportionality constant. Okay, just take note that if you're using A, alright, so A refers to the absorptivity. Okay, absorptivity is a factor that tells you how absorbing your sample is. towards a particular wavelength of radiation within the UV-Vis region, okay, used for the analysis. So normally, the higher the absorptivity, or the molar absorptivity for that matter, it means to say that your sample is more absorbing. Alright? Um, Especially molar absorptivity, this can be used actually for qualitative purposes. Okay, the value for molar absorptivity, especially for organic compounds, is recorded in compendia. Okay, and can serve as identification marker for that particular molecule. Okay, now take note that if you're using absorptivity, okay, if you're using absorptivity, the unit for concentration should be in grams per liter. If you're using molar absorptivity, the unit should be in molarity. Okay. What else? So absorbance is a dimensionless quantity, but typically they like to write AU. AU just means arbitrary units, no? Kunwari ang units. Sa mga Tagalogin. Okay. Now in older books, absorbance is sometimes referred to as your optical density. Okay. Whereas absorptivity is referred to as your extinction. Okay, extinction coefficient. So molar absorptivity is your molar extinction coefficient.